I'm Edgar Madrill.
I'm Fletchy Cooper.
I'm Matt Berry, and this is LAB2, Gaussian Beam Profiling and Propagation.
Oh, so we started the lab by setting the optical axis of the laser to the optical axis of this rail. And we did this with a pinhole. So we put the pinhole really close and used the X and Y translation. And then we moved it farther back and used the angular rotations to center the beam onto the pinhole. We did this repeatedly until the light was on axis with the rail. The next thing we did was align the microscope with the laser. We sent the laser through the microscope objective. We used a smaller numerical aperture to get a long working distance. That way we can view the image far away. And we started off close in similarity to what we did to align the optical axis of the laser. We brought it close and aligned the objective in the X and Y translation. Then we moved it out farther away and used the tip and tilt. And then we used different translations to move the actual beam and the tip and tilt to move the crosshairs. And right there is the crosshairs aligned to the axis of the laser.
Alright, this is the next part of our lab where we're measuring the profile of our beam. We already have it aligned with the table, and we're using a knife edge to cut off part of the beam and then pass it into a photodetector to measure how much light is getting through. So the first thing we did is align our knife edge with our laser surface, focusing a microscope first on the laser surface, then on the knife edge to make sure they're aligned with each other, and then putting a photodetector behind the knife edge. To measure the Gaussian profile, we move the knife edge starting completely blocking the beam, and then we move the knife edge away so that more light can get in the photodetector to create our beam profile. In the start of the lab, we started making measurements in increments of 10 microns, and we calculated based on the size of our beam diameter that we would have had to take over 1,000 measurements at that rate. So we stepped it up to 50 micron steps. So we only had to take 200 points to get our Gaussian profile, and we ended up plotting our data. And if we look down here, we see the Gaussian profile starts with almost no light getting through, and then as we move through our knife edge to the point where all the light is getting through to the profile. Right. So for our setup, I want to talk a little bit specifically about how we align the lens with our laser. We wanted the surface of the laser and the front surface of the lens to be separated by exactly 400 millimeters. To do this, we focus the microscope onto our laser surface, and then we move the microscope back 400 millimeters from its original position and move the lens so that the microscope could focus on the back surface of the lens to ensure that the lens and the laser were separated by 400 millimeters. And then from here, the only compensation we need to make is to move the lens slightly back so that instead of focusing on the back surface, we're focusing on the front surface. So we just adjust by the thickness of the lens.
After placing the lens and the microscope in the correct locations as Matt previously discussed, we aligned the lens relative to the lens the same way we did in Lab 1, so that the back reflection was on the surface of the laser. After this was done, we wanted to locate the beam location, the beam waist location of our laser. So what we did was we translated the microscope until our output was collimated. This found the beam waist because at the beam waist we have plane waves, therefore our output will be collimated. Once this was estimated, we placed the knife edge before the beam waist and took measurements as we translated the knife edge in the X direction. After we're done taking these measurements, we placed it after the beam waist.
Okay.
So this is our result for the knife edge being placed before the beam waist. As you can see, we get close to 0 when the knife edge is completely blocking the beam, and as we translate through, we begin to see more of the output power until finally it flattens out because we get all of the laser through.